Hello everyone, this is lecture 7. Still in this lecture, we will talk about a system of different equations, and we're going to use the system to model prey and predator interactions. We're going to use this system of different equations in lecture 6, modify this system to include some other terms in order to make the problem more realistic. So the learning objectives of this lecture is obviously we're going to model various prey and predator scenarios using system of different equations. So I'm going to break this lecture down into 3 different sections. So the first section is I'm going to quickly go over the classic prey and predator model and the result of equilibrium values. Then I'm going to move on to the second section where I modify the classic prey and predator model to include the prey refuge terms. Then we're going to look at the equilibrium of the model and also visualize the results using Excel. Then I'm going to move on to the last model where I modify the classic prey and predator model where instead of the population of the prey increase exponentially, now it's going to increase logistically. That is, there is a carrying capacity on the populations of the prey. So for the first sections, the classic prey and predator model that we analyzed in lecture 6 is given as R sub n plus 1 minus R sub n equal to K1 times R sub n minus alpha times R sub n times F sub n, and F sub n plus 1 minus F sub n equal to negative K2 times F sub n plus beta times R sub n times F sub n. For R sub n is the population of rabbits at time period n, and F sub n is the population of foxes at time period n. In addition to that, you have the parameter here in the system where K1 is the natural growth rate of rabbits in the absence of foxes, alpha is the attacking rate of foxes, or you can think of that as the death rate of rabbits in interactions with foxes. And K2 is the death rate of foxes in the absence of rabbits, and beta is the growth factor of foxes due to the presence of rabbits. And again, in lecture 6, we spent time in analyze the equilibrium values, and we obtained 2 equilibrium points. The first one is the trivial solutions, that is R, F is equal to 0, 0. In this scenario, both rabbits and foxes population die down. And the second equilibrium point is R, F equal to K2 over beta, K1 over alpha. When you have R equal to K2 over beta, it means that at equilibrium, the prey population is determined by how quickly the predators die compared to how much they reproduce from consuming the prey. And you have F equal to K1 over alpha. So the populations of foxes or predator in this case, or predator, at equilibrium depends on how fast the prey reproduce and how effectively the predators can catch and consume the prey. Now, from this classic model of prey and predator interactions, what I'm going to do is I'm going to modify the system by include some of the assumptions in the model so that my hope is to make the model more realistic. So some of these assumptions that you see here is already occurring in lecture 6, right? So for there are 2 types of text here, the regular text and italic text. So the italic text are the new assumptions that we need to include in our model. So the second model we have here is the prey and predator model with prey refugees. So the first assumption is that there is enough food for rabbits and the population in rabbits increases by a constant rate in the absence of foxes. And as we know, as the difference of change increase or decrease at the constant rate, it can be related back to exponential functions. In this case, is the exponential growth. In the second assumption, you have the rabbit's population decreases as a result of interaction between rabbit and foxes. However, we want to include some new information here, a new assumptions, that is, in reality, it is often the case that some rabbit individuals can escape foxes by hiding in refuges, such as burrows. Thus, there will always be at least a few rabbit individuals surviving from the attack of foxes. Right? So these survivors, of course, could potentially breed and replenish the rabbit populations. Right? So we have new assumptions here that the rabbit will not be there in the open area. Sometimes they will seek refugees and they go in hiding, and therefore the predator or the foxes in this case will not be able to consume the prey or the rabbits as often as they want compared to the classic model. Now for the third assumption, it's very similar to the classic case that the rabbit population is the only source of food for the foxes. Therefore, in the absence of the rabbits, the population of the foxes decreases by the constant rate and die down, and this is related to exponential decay. For number 4, assumption 4, the fox's population increases as the result of the interaction between the rabbit and foxes. However, this interaction is limited due to refugees, as mentioned earlier in assumption 2. The rabbit will not be in the wide open area. They will seek refugees in the moment of dangers, and therefore foxes will not be able to consume rabbit as much as they can in the classic model. And for the last assumptions, no interaction with other species. Still, we want to look into the interaction between one prey and one predator only. Also, there is no immigration or immigration from or to the forest. So there is no immigrations or immigrations from to the forest. No harvest and hunting is allowed in this scenario. Similar to the classic case, we're going to say that R sub n is the population of rabbits at time period n, and F sub n is the populations of foxes at time period n. Now we're going to use these assumptions to build up the model for the rabbit populations and for the fox populations, and then include this scenario into one system, and we call that the system of difference equations in the context of prey and predator model with prey refugees. So from assumption 1, it say that there is enough food for the rabbits to survive in the forest, and the populations of rabbits increases by the constant rate in the absence of foxes, and this increase by a constant rate relates back to exponential growth. From the assumption 1, we have that the change in populations of rabbit R sub n plus 1 minus R sub n is equal to k1 times R sub n, where k1 is the natural growth rate of rabbits in the absence of foxes. And we assume the parameter k1 has to be a positive number. Now from assumption 2, you have that the rabbit population decreases as a result of the interaction between rabbit and the foxes. So from assumption 2, you're going to modify this equation to include the interaction between the rabbit and foxes. And when there is the interaction between the two species, the rabbit population will decrease. And you have alpha multiplied with R sub n times F sub n, right? So very similar to the classic model. In this case, alpha is the attacking rate of foxes, or can be considered as the death rate of rabbit in the presence of foxes. However, there's another information in the second assumption that most of the time the rabbit individual seek refugees go into hiding, and so that you need to include that term in the model. Instead of alpha times R sub n times F sub n, you need to include the refugee term, that is alpha times 1 minus c times R sub n times F sub n. So c in this case, the fraction of prey in refuge protected from predation. So you have alpha is the attacking rate, and alpha is assumed to be a positive number. C in this case is the fraction of the prey in refuge protected from predation. And that's it for the model of rabbit populations. So I call this equation 1, and I will include this equation in the system of different equations to model the prey and predator interactions. Now I'm going to move on to the next two assumptions, where I'm going to use the assumptions to model the fox populations. In assumption 3, the rabbit population is the only food source for the foxes. Therefore, in the absence of the rabbits, the population of the foxes decreases by a constant rate and dies out. So from assumption 3, you have that F sub n plus 1 minus F sub n equal to negative k2 times F sub n, where k2 is the death rate of foxes in the absence of rabbits. And we assume that k2 is a positive number. Then we're going to move on to assumption 4. The fox population increases as the result of the interaction between rabbit and foxes. However, this interaction is limited due to refugees. So from assumption 4, you're going to modify this initial equation, that is F sub n plus 1 minus F sub n equal to negative k2 times F sub n. And the populations of foxes will increase due to the interaction between rabbit and foxes. So you do beta times R sub n times F sub n. But remember, this interaction is limited due to refugees. So you need to include the term 1 minus c in the equation. So beta times 1 minus c times R sub n times F sub n. In this case, again, beta is growth factor of foxes due to the presence of rabbit. And you assume that beta is a positive number. And this is the second equation in the system of different equations that we need to use for the model. Then we have that from equation 1 and 2. We have the system of the form R sub n plus 1 minus R sub n equal to k1 times R sub n minus alpha times 1 minus c times R sub n times F sub n. And from the second equation, you get f sub n plus 1 minus f sub n equal to negative k2 times f sub n plus beta times 1 minus c times r sub n times f sub n. The difference between this model and the classic model is the refugee term 1 minus c. If c is equal to 0, we get back the classic model. So if c is equal to 0, the model becomes the classic prey and predator model. Now in the case of c equal to 1, if c is equal to 1, that is the case where all the rabbits go into hiding and there's no more food for the foxes to consume. So therefore, the rabbit population will increase exponentially to infinity, and the fox population will decrease and die out from the ecosystem. So here, if c is equal to 1, all the prey go into hiding, then the fox populations will decrease to 0. Okay, so that's some extreme cases that we can consider. In practice, you can choose the value of c to be between 0 and 1. C can be 30% or 0.3 for that matter. That means there are 30% of the rabbit population go into hiding. Or if you choose c to be equal to 70%, that is 70% of the rabbit population go into hiding from the presence of the predator. So next, we're going to solve for the equilibrium values of this system of difference equations. So similar to the classic model, to find equilibrium values, what we do is we set r sub n plus 1 equal to r sub n equal to r, and that is the equilibrium for the rabbit populations, and that is what we're going to find. In addition, we're going to set f sub n plus 1 equal to f sub n equal to f, and that is the equilibrium value for the fox populations. So to find equilibrium value, we set r sub n plus 1 equal to r sub n equal to r, and f sub n plus 1 equal to f sub n equal to f, and we're going to substitute r and f into the system. And this is the system that we're going to use to solve for the equilibrium values. So I substitute r and f into the first equations. I'm going to get r minus r on the left hand side equal to k1 times r minus alpha times 1 minus c times r times f. So on the left hand side, this is going to be 0. On the right hand side, r is a common factor. Then we have r times k1 minus alpha times 1 minus c times f. And from here, you have that either r equal to 0 or f is equal to k1 over alpha times 1 minus c. Similarly, when I substitute r and f into the second equation, this is what I'm going to have. F minus f equal to negative k2 times f plus beta times 1 minus c times r times f. On the left hand side, I got 0. On the right hand side, f is a common factor, and I have f times negative k2 plus beta times 1 minus c times r. Here you got either f equal to 0 or r is equal to k2 over beta times 1 minus c. So you obtain two equilibrium points. So here we obtain two equilibrium points. So one of which is r, f equal to 0, 0. Again, this is a trivial solution where everything will die down. I mean, both rabbit and fox's population will die out from the ecosystem. And another equilibrium point, that is r equal to k2 over beta times 1 minus c, comma k1 over alpha times 1 minus c. Right, this is a non-trivial solution. So the term r equal to k2 over beta times 1 minus c can be explained as this is the prey population or the rabbit population that is influenced by the balance between how quickly the predators die in terms of k2 at the rate of k2 and how efficiently they grow from consuming prey with the rate of beta. Now this result is adjusted by the refuge term of 1 minus c. So for r equal to k2 over beta times 1 minus c, or the rabbit populations, is influenced by the balance between how quickly foxes die at the rate of k2 and how efficiently they grow from consuming rabbits. at the rate of beta. And of course, the result adjusted by the refuge of 1 minus c. On the other hand, you have that f is equal to k1 over alpha times 1 minus c. So the fox population depends on the growth rate of rabbits at the rate of k1 and how efficiently foxes can consume at the rate of alpha, adjusted by the refuge of 1 minus c. So that is the equilibrium values for the case of prey and predator model with prey refugees. And now we're going to look into visualizing the solutions of the system, and I'm going to use Excel to help us analyze the model and visualize the result of the model. Right, so this is what you see in lecture 6. This is the classic model. This is the solutions of the classic model. Now I'm going to move on to another model. So here I'm going to change the sheet name from sheet 1 to model 1. Then I choose another, or I add another sheet, and I call that model 2. And model 2 is the one that we're looking at in lecture 7. So first I'm going to read column, the time column, where we have the time period. We have the initial value, initial time, which is 0. And the populations of rabbit at this initial time is, let's say, 500. Depends on the scenario, depends on the problem. You may have a different value of rabbit populations and of fox populations. So foxes, in this case, let me choose 100 foxes in the system. Now I want to observe the behavior or the interaction between these two species for 600 time periods. Right? I show you how to create the 600 rows last time. So here it goes again. So you said move on to the next row, hit equal. You do sequence, time sequence, open the parentheses. Here you can see some options in the sequence here. So the first option is the number of rows. So you want obviously 600 rows. How many columns do you like to have? In this case, it's just one column because it's just the time column. The starting number is 1 in this case, and the stepping number is also 1. So you do 600, comma 1 column, comma 1 for the starting number, and the stepping is just 1. So you want to take one step at a time. Close the parentheses, hit enter, and this should automatically create a list of 600 numbers for you, or 600 rows for you. Okay, so now for the populations of rabbits, we're going to use the system of different equations we have in the lecture. So the system should look like this. So r sub n plus 1 equal to r sub n plus k1 times r sub n plus alpha times 1 minus c times r sub n times f sub n. So best is the populations, rabbit populations. And for fox population, you have f sub n plus 1 equal to f sub n minus k2 times f sub n. This is negative. So minus alpha times 1 minus c times r sub n times f sub n. And here you have plus beta times 1 minus c times r sub n times f sub n. And you know the value r0 in this case, 500. Well, just follow this formula to type in the values that you need to find the rabbit population at time period 1. So I'm going to start with r0, which is 500 in this case, plus k1. And in the formula, you see we have multiple parameters that we need to provide the system so that we can do the calculation. So let me get out of here. So let's start k1 should be 0.04. Alpha value should be 0.004. K2 is 0.08. Beta is 0.0002. And C, in this case, I'm going to choose 0.03. So 0.03 for C means that there are just 3% of prey who go into hiding when they encounter foxes. Right. I'm going to type in the formula here. So this is equal to R0 plus K1 times R0 minus alpha times 1 minus C, close parentheses, times R0 times F0. You need to keep the parameter the same throughout all of the calculations. So you do $I, $2, $I, $3, and $I, $6. And you double click on the formula and it should track it down for you automatically. So that's the rabbit populations. Now I'm going to move on to fox populations. So fox populations F1 equal to F0 minus K2 times F0 plus beta times 1 minus C times R0 times F0. So type that into Excel. So F0 minus K2, which is here, times F0 plus beta times 1 minus C times R0 times F0. Then you're also going to stabilize the value of parameter or keep the parameter the same throughout all the calculations. If I put the dollar sign in front of I, dollar sign in front of the number like that. And here, the cross is changing from white cross to black cross here. Double click on that, it's automatically go down to 600 time period. Right, it depends on the cell that you choose to have the value. So in this case, I have I2, I3, I4, I5, and I6. So I want those numbers to stay the same throughout all the calculations. That's why for, let's see, I2, I put dollar sign in front of I, dollar sign in front of 2. Now let's visualize these results. Okay, I want to plot two graphs. The first one is the populations of foxes and rabbits versus time, and the second plot is the interaction between rabbit and foxes. So I just want to see the population between rabbit and foxes without time periods. Okay, so for the first plot, again, here's that's. I'm going to choose the first row here to select all of the 600 rows. You just choose the first row, hit Shift, Control, downward button, and it's automatically select everything for you. Now just scroll up because you want to place the plot next to the table. So I'm going to go to Insert, Scatter Plot here. This is what you should see. And I'm going to change the layout. So click on the plot or the graph, go to Quick Layout, and choose the first layout, layout 1. So that I have the title for the x-axis, the title for the y-axis, the legends, and also the title for the entire graph. So the title for the graph, I changed that to Prey Predator in the Refuge model. Refuge model. The title on the x-axis, I changed that to rabbit population. Change that to time. And the y-axis title is population in general. And for the legends, I click on the legends here and go to select data, and I'm going to change the name of the series. So series 1, I changed that to rabbits, and series 2, I changed that to foxes. To show that the blue curve is the populations of rabbit and the orange curve is the population of foxes, and that's how it behaved over 600 time periods. Okay. Now, just to visualize the interaction between foxes and rabbits, what you do is you just choose the last two columns in our table. So here, I'm going to choose 520 and use the combination of these three keys on the keyboard, Shift, Control, and downward button. And just scroll up so you can place the graph right below the first one. So you go to Insert, Scatter Plot here, and this is what you should see. I'm going to change the layout of the graph a little bit. So I go to Quick Layout and choose the first layout or layout 1. Delete the legends. Right, we don't need the legends for the second graph. The x-axis title is rabbit population, and the vertical axis title is fox population. Now, also from our analysis in the lecture notes, we come up with the equilibrium values for rabbit populations and fox populations. Let's give that a calculations. You see, depending on this parameter, what is the equilibrium value of R and what is the equilibrium value of F. From the note, we get R equal to K2 divided by beta times 1 minus C, and F is equal to K1 over alpha times 1 minus C. So I'm going to go up here, and I'm typing R equilibrium, and I'm just going to type in this formula. So K2 over beta times 1 minus C, so this is equal to K2 over, open parentheses, beta, times, open parentheses again, 1 minus C, close parentheses. So C should be this one. Okay. So that. So based on this parameter, the value of R at equilibrium is around 412. And we're going to do the same for F equilibrium. We have this equal to K1 divided by open parentheses, alpha times 1 minus C, close parentheses, and that should be the value. So F equilibrium is around 150. So go back to, let me move this over here. So you have the initial value at this point, 500, 120, and the equilibrium point is around here in the middle. And from the initial value, it spiral around the equilibrium point and spiral outward. Indicate that the equilibrium point is something called the unstable point or unstable equilibrium point. Next, we're going to move on to the third prey and predator model. In this model, we will include a prey carrying capacity. So that is, as the population reaches this carrying capacity, the populations of rabbit will remain at that level as time goes on. So we're going to have the assumptions as always. The first assumption is that due to the limitations of food for rabbits, the rabbit population follows a logistic growth model in the absence of foxes instead of an unrealistic exponential model. Because in reality, populations cannot grow to infinity. It has to grow to a certain level because of the limitations of food in the area. The other four assumptions are going to be very much the same compared to the classic model. That is, the rabbit population decreases as the result of the interaction between rabbit and the foxes. The rabbit population is the only source of food for the foxes, therefore in the absence of the rabbits, the population of the foxes decreases by a constant rate and dies down. And number four, the fox populations increases as the result of the interaction between rabbit and foxes. And number five, no interaction between other species. Also, there is no immigrations or immigrations from or to the forest, and no harvest and hunting is allowed in this ecosystem. Now again, we're going to name R sub n to be the population of rabbits at time period n, and F sub n is the population of foxes at time period n. We're going to use the first two assumptions to model the rabbit populations, and assumption 3 and 4 to model the fox populations. So from assumption 1, you have that R sub n plus 1 minus R sub n to be equal to k1 times R sub n. But remember, this is no longer an exponential growth, but a logistic growth. So you do have k1 times R sub n times 1 minus R sub n divided by L, for L is the carrying capacity in this case. So k1 is the natural growth rate of rabbits in the absence of foxes, but also L in this case the carrying capacity. Now we're going to use these equations, modify the equations a little bit to include the interaction between rabbit and foxes. So from assumption 2, you have that R sub n plus 1 minus R sub n equal to k1 times R sub n times 1 minus R sub n divided by L minus alpha times R sub n times F sub n, for alpha again in this context is the attacking rate of foxes. And alpha is assumed to be a positive number. So I called these equations, I just got equation 1, and I will include this equation in the system of different equations. From assumption 3, I have that the rabbit population is the only source of food for the foxes, therefore in the absence of the rabbits, the populations of the foxes decreases by a constant rate and die down. So F sub n plus 1 minus F sub n equal to negative k2 times F sub n. For k2 is the death rate of foxes in the absence of rabbits, and we assume k2 to be a positive number. From assumption 4, we're going to modify these equations to include the interaction between foxes and a rabbit. That is, the fox population increases as a result of the interaction between rabbit and foxes, and therefore you do add beta times R sub n times F sub n, where beta is the growth factor of foxes due to the presence of rabbits, and we assume that beta is a positive number. And this is the second equations that we need in the system of different equations. So from equation 1 and 2, we have the following system. That is R sub n plus 1 minus R sub n equal to k1 times R sub n times 1 minus R sub n divided by L minus alpha times R sub n times F sub n, and F sub n plus 1 minus F sub n equal to negative k2 times F sub n plus beta times R sub n times F sub n. Now, as usual, the next thing that we do is we're going to find the equilibrium values of this model. Right? To find the equilibrium, so we're going to set R sub n plus 1 equal to R sub n equal to R, and F sub n plus 1 equal to F sub n equal to F, and we're going to find the value of R and F from this system. So to find the equilibrium values, we set R sub n plus 1 equal to R sub n equal to R, and F sub n plus 1 equal to F sub n equal to F. Then we're going to substitute R and F into the system, and here's what we got. So R minus R equal to k1 times R times 1 minus R over L minus alpha times R times F. On the left hand side, we get 0. On the right hand side, R is a common factor. So you're left with k1 times 1 minus R over L minus alpha times F. So in this case, you have that either R is equal to 0 or K1 times 1 minus R over L minus alpha times F equal to 0. And you solve for F in terms of R in this case. So alpha times F equal to K1 times 1 minus R over L. And you divide both sides for alpha, you get K1 over alpha times 1 minus R over L. So this scenario is going to be a little bit different from what we have seen in the last two models. In this case, the value of F depends on R. So next we're going to substitute R and F into the second equations, and we get F minus F equal to negative K2 times F plus beta times R times F. On the left hand side you get 0, on the right hand side F is a common factor, and you're left with negative K2 plus beta times R. Here you get either F equal to 0 or R is equal to K2 over beta. So you also obtain two equilibrium values or two equilibrium points. So we obtain two equilibrium values. The first one is the trivial solutions R, F equal to 0, 0. So this is the trivial solution. And for these solutions, the populations of rabbits and foxes will die out from the ecosystem. And we're going to have R, F to be a non-trivial solutions, where R is equal to K2 over beta, and F depends on the value of R we just have, which is K2 over beta. So that is F is equal to K1 over alpha times 1 minus R over L. For R in this case is equal to K2 over beta, so you do K1 over alpha times 1 minus K2 over beta over L. So for the value of R equal to K2 over beta, the explanation for this is again the prey population of the rabbit population is determined how quickly the predators die at the rate of K2 compared to how much they can reproduce from consuming the prey at the rate of beta. And for the solutions of foxes, F equal to K1 over alpha times 1 minus K2 over beta divided by L. So there are two parts to the solutions. The first part of the solution is K1 over alpha, showing that if the prey grows fast and the predators are not very efficient at hunting, the predator population need to be larger in order to balance out the ecosystem. And the second part is 1 minus K2 over beta altogether over L, tell us how predator population is limited by the prey's carrying capacity. So if the ecosystem cannot support many prey, for small L for the small carrying capacity, or if predators die quickly with large K2, fewer predators will be able to survive in the ecosystem. So that is the explanations of the terms in the equilibrium points that we obtain here. Now we're going to move on to using Excel to visualize the results that we get. So here is our model 1 and model 2. I'm going to click on this cross button for another model. So I call this model 3. Bring this up, zoom in a little bit. So again, I will create 3 different columns here. The first column is for time period, the second column is for rabbit populations, and the last column is for fox populations. So this is time, rabbits, and foxes. So you can start at 0. The initial number of rabbits should be, let's say, 500, and the initial value for foxes should be 120. Let's start with that. You want to observe the populations up to 600 time periods. So again here, hit equal, type the command sequence, open parentheses, I need 600 rows, 1 column starting at 1 with 1 step at a time. Alright, so I'm gonna write down the formula up here so that we can type into Excel. So you have R sub n plus 1 equal to R sub n plus K1 times R sub n times 1 minus R sub n over L minus alpha times R sub n times F sub n. And F sub n plus 1 equal to F sub n minus K2 times F sub n plus beta times R sub n times F sub n. So you need some parameters, the value of the parameters, right? You need K1, capital L, alpha, K2, and beta. So the value of K1, K2, alpha, and beta should be the same. Let's just use the same information that we had before. So K1 is equal to 0.04, alpha is 0.004, K2 is 0.08, beta is equal to 0.002. The value of L, let's say 500. Let's say 1,000. So starting population of rabbit is 500, but you set or limit the carrying capacity up to 1,000. So the rabbit population could not exist at that value 1,000. Now I'm going to type in the model the solutions for rabbit at time period 1. Okay, so R0 plus K1 times R0, so times, open parenthesis, 1 minus R0 divided by L, close parentheses, minus alpha times R0 times F0. So that. And remember, you don't want the value of the parameters here to change in the calculations, so you're going to set $sign here. So for the fox populations, I have F0 minus K2 times F0 plus beta times R0 times F0. And I'm not going to change the parameter. So we got the populations of rabbits at time period 1 and the populations of foxes at time period 1. So now over here, when you move the cursors change from the Y cross to black cross, and then double click on that. The formula should automatically drag it down to time period 600, and you're going to do the same for the fox populations. Alright, so now you want to visualize the results that you just generate. So what you do is, so there are two plots that we want to graph. The first one is the graph that showed time periods versus the populations of both rabbits and foxes. And the second graph is the population interactions between rabbits and foxes. So for the first graph, I'm going to choose the first row here, use the combinations of Shift, Control, and that word button to choose all the value in the 3 columns. Now you go to the right-hand panel. You scroll up all the way up so that you can place the picture right next to the table. So you hit Insert, go to Scatter Plot here, and Scatter Plot with smooth lines and markers. So click on the plot to change the layout and choose Layout 1. So the title of this plot is Prey Predator with a prey carrying capacity. See, the axis title in this case, the time period, the vertical axis title is population. And you're going to change the series here to reflect the rabbit populations and the fox populations. So click on that, choose Select Data. Now you have 2 series. Series 1 you change to rabbit, and Series 2 you change to foxes. And hit OK. And this is the graph that you can see the populations of rabbits and foxes behave over time. In this case, 600 time period. And it looks like the population tend to stabilize around 400 for rabbits and around 80 or 90 something for the fox populations. Now to see that stabilizations or the equilibrium value, I'm going to do the calculations here. So for R equilibrium, R is equal to K2 divided by beta. So you have 400, the equilibrium value for rabbit population is 400. And for the fox equilibrium, you have the formula to be, this is equal to K1, so open parenthesis, K1 divided by alpha, close parentheses. So that's the first part of the solutions. Multiply with the second part, which is 1 minus the fraction. So I'm going to times the numerator now. So open parenthesis for the numerator. So K2 divided by beta. Right, so that's numerator altogether divided by the denominator, which is the carrying capacity L. Now you close parenthesis to end the second part of the solutions. You hit enter and you should get the solutions for F equilibrium. So in this case, F, the number of fox, we reach 60. Okay, so now let's visualize the interaction between rabbit population and fox populations only without time period. So here to choose the value, I'm going to choose this 2 columns, or the first row of this 2 column. Use the combination of Shift, Control, that word button. And then again, you scroll up here and insert, scatter plot here. And I'm going to change, let me place the picture over here. Click on the graph, go to Quick Layout and change that to Layout 1. Delete the legend, so we don't need the legend in this case. The chart title should be rabbits versus foxes. And for the x-axis title, you have rabbit populations. And for the y-axis title, you have foxes populations. So now let's make this graph a little bit bigger so that you can see the initial value. So it's somewhere in here. Let me delete this. So the initial value of rabbit population is 500, and of the fox population is 120. So it's around here, right? So this is the initial conditions, and the equilibrium values is around 400,60. So this picture is a little bit different from the last two examples that we have. That is, from the initial value, the curve tends to spiral inward toward the equilibrium point. And if you have this scenario, this is called a stable equilibrium point. That means in this model, there's interaction between prey and predator, the interaction between rabbits and foxes, and in the ecosystem, the population of the two species tend to reach the equilibrium at 460 for rabbit and foxes respectively. So that's it for me. Please let me know if you have any questions. Thank you.